polished. Recording permission with the warning that you shouldn't expect a polished lecture to use for mass distributions. So take it with your own risk. So here we are. So okay, it's a pleasure to meet with you and discuss some math. So this joint work with Jesus Rebollo Bueno and Petros Valettas. We didn't put it on archive yet, but hopefully in the summer we'll have time to, clean it up and put it on archive. So it's somewhat basic questions. And I was surprised this stuff is not already known. And I searched literature and I'm going to tell what I find that is known. And almost everything we do is from scratch, more or less. And I'm going to try to tell you the ideas, there will be theorems, algorithms, and, the ideas behind those theorems and algorithms. Okay. All right, so we got a vector with n coordinates here, right? And the first thing there is I take tensor product of this vector with itself d times, right? By the way, I guess you hear me well and everything is all fine. I didn't ask that part. Okay, great. Okay, and then, the first thing I write there is like you take tensor product of this vector with itself like d times, and you got what I just wrote there, right? And then the second object I talk about is you take a linear form, since your v is a vector with n coordinates, you can take inner product of it with an x, which has n coordinates, right? Raise it to the power d, and you get what I wrote there. And when you look at it, you would see, they look very similar. They almost look like the same. If you would identify this a tensor type thing on the first one with the monomial type thing in the second one, they would look almost the same thing, right? So the second one is a degree d polynomial. The first one is a degree d symmetric tensor. And I try to write it down. So the first object is a rank 1 symmetric d tensor, and the second object is a rank 1 degree d homogeneous polynomial. So if you want to talk about symmetric tensor rank over the reals, first object is your kind of atomic object. You try to add that and build up more complicated objects, right? And if you want to talk about some notion of rank for homogeneous polynomials called Waring rank, which I'm just going to define, you think about the second object. So I'm going to talk about polynomials during the rest of the talk, but if you're somebody who cares about symmetric tensors, whatever I say has an equivalent, statement for real symmetric tensor rank. Okay. All right. So this is just the first thing to start off with. So here's the Waring rank definition. So I have my vector space, which is this space of homogeneous degree d polynomials with n variables. This P and D is my vector space. And I have an object. My object is here, this little guy, right? And then the Waring rank of this input is the smallest number m, right? Such that you can decompose your input P into summation of this rank 1 objects, your atomic objects. And here I want to put the constraint that these vectors that I'm using to construct my rank 1 objects have unit norm. This is not, this is not a big deal. This you can always assume if you like to. And for the rest of the talk, this is what I'm going to do for convenience. So my vectors that I construct rank 1 forms have unit norm, or in other words, they come from the sphere. Okay, that's my Waring rank. The smallest number of atomic elements I could use is called Waring rank. All right, pretty good. Now, what do we know about this? So Waring rank over complex numbers, not over the reals, is subject of this big theorem due to Alexander and Hirshovich. Actually, like a couple of papers. So they, figured out if you would do the same definition over complex, not over the reals, what would be the rank of an object generically. Okay, that's called Alexander-Hirshovich theorem, but it doesn't answer our question over the reals. But if you add an observation by Blackman and Tytler on top of the big theorem by Alexander and Hirshovich, you get the answer for what we were interested in. So I'm going to try to parse this down. The Waring rank of the object is typically, I'm going to tell what is typically, between these two numbers. Okay, and there are some exceptions. This theorem does not hold if your degree is 2, it has to be bigger than 2. And if your degree is bigger than 2, all the exceptions are the ones that I wrote here. Actually, a big part of the effort was trying to clarify all the exceptions precisely. So this is, if you take this big Alexander Hirschowitz theorem and this very nice paper by Bleckerman and Teitler, they give you an answer for real Waring rank for typical case. And typical means the following: the rank estimate that you're getting should be realized by a set of symmetric tensors or homogeneous polynomials, and the set should not have measure 0. It has a set which has an interior. Think about it that way. Okay, so that's what a typical object is, and they have these estimates. And as you see, the estimates are kind of pessimistic. So in the sense that already the dimension of the vector space is this combinatorial thing I wrote there, n plus d minus 1 choose d. And already the dimension is an upper bound for your rank. We know this atomic objects create a basis. Even by linear algebra, I can get the dimension. Okay. So, and the estimate you get after all this, a lot of work is roughly speaking 1 over n times the dimension. Okay. So now, this, to me, calls for the following question. If I can allow an epsilon room of error in the decomposition, instead of asking the question exact, my decomposition here was exact, right? If I allow a little bit of an error, can I possibly have better estimates, right? So here is the definition. You give me a norm that you like on this vector space, and you give me an epsilon, which is your, tolerance for the error, right? And then what I do is this: I go look for your input is this p. Right? I go look for q, which is epsilon close with respect to the norm you picked, and I try to look for the q with minimum Waring rank. So basically, you draw an epsilon ball around your input p, and then you say, okay, what is the smallest Waring rank realized in my epsilon ball? And then my goal is to quantify the effect of giving this epsilon room of error on the rank estimates. A priori, it's not clear if I'm going to get anything better than what is already known. Maybe allowing error doesn't help me at all. Who knows? Maybe exact is what it is. Or maybe I can get something. So that's the question. I want to first quantify how much I could gain. Second, not only quantify, I would try to find algorithms that gives me at least a good approximation of this decomposition with epsilon error. Ideally, I would like to find the minimum q in the epsilon ball. If not, let me try to get something that gets close to. Right. So that's kind of what I have in mind. And any questions so far?
No, sounds good.
All right, awesome. So
the optimization is over the polynomials, right? So you're looking for polynomials such that
exactly, polynomials. So I have a polynomial p, right? And I draw an epsilon ball around my polynomial p. So let me see if I have any. Yeah, here I think this is my p. And you pick the norm you like.
Mm-hmm.
And draw an epsilon ball around that p, depending on the norm you pick. And I'm trying to find the q here, which has small Waring rank. That's exactly what I'm trying to do. And so we started a bit late, and I guess 40 to 45 minutes was the talk. So until when I should go, like 50 something? Ali, what's?
Well, 250 would be good.
Okay, I'll try to end up at 250 then. Awesome. Right. So that's my goal. And now here is the outline of the talk. I'll first talk about some basic geometry of this vector space. And then I have 2 theorems and corresponding algorithms. we called these algorithms, one of them called randomized greedy approximation. The other one we called Morey sparsification. Morey is somebody who works in Banach space theory, but we used his ideas from 70s. So I don't think he has any interest in building these algorithms, but his ideas was very, very useful. So that's what we call them. And the ideas behind these theorems and algorithms is the first one, the randomized greedy one. We used an idea coming from additive combinatorics called energy increment method. And the second one, this Banach space theory, or more precisely, local theory of Banach spaces, people call it type 2 constant of a norm. You don't need to worry about what this type 2 constant. I'm going to try to tell you what is the idea coming out of this, a lot of work that these people have done in the 70s. And if we have time, I don't think we will have time. If you would have time, there is also some fun you could have on this subject using Frank-Wolf type algorithm, like constraint gradient descent. It's not algorithmically efficient, but it gives you a nice theorem. So that's, but probably I'll skip that part. Okay, that's kind of the outline. Some geometry, statement of theorems and algorithms that we got. And then I'm gonna try to tell you, the intuition behind how does this work. All right, so here's the basic geometry part. So you got a convex body, centrally symmetric. And then whenever you have a convex body on any real space, I called it here R to the capital N, but it doesn't matter. It gives you a norm. So how does it work? Let me try to illustrate this. So let's say, let's say this is my convex body K, right? And I got an F here. This F is not inside this convex body K. Now I'm going to try to enlarge my K to include F, right? Suppose I enlarged it like twice, and there will be some bad drawings. But since somebody published a paper called Math with Bad Drawings, it's not a shame anymore. So I can do this. So let's see. There's a book, sorry, not a paper, on Math with Bad Drawings. Let's say 2 times K looks like this, and F is precisely on the border. Then this would mean the K norm of this F is 2. It's like, K is going to be your unit ball. As long as it's centrally symmetric, probably my drawing is not centrally symmetric, sorry for that. You have to have somebody symmetric with respect to the origin, then you keep enlarging it until it includes your input F. That's a norm, right? Okay. And then you usually need to also have an inner product. Here's my inner product. In Rn, we use standard Euclidean inner product or some other inner products. And as long as you have an inner product, every convex body K has a dual called like polar body, which means you think about all Y. Okay, I was working in R capital N. This has to be R capital N, right? Such that I take any X in K and all this, and I think about all Y's such that X times Y should be always less than or equal to 1. That's the polar convex body. And here I found a picture from Kepler's 17th century book, which shows you the dual of a cube with this definition is the cross polytop. Some cute picture here. So, or more precisely, now let's also think about the norms coming out of it. I'm going to get to this point in 1 sec. Let's just do the example. So L infinity is the cube. L1 is the cross polytop. Okay. And then I think you can agree with me if you have a vector and you're looking at the L1 norm, which is, absolute values, sum every coordinate, right? We all know what is L1 norm. That's the same as look at all the vectors in the cube, take an inner product with your vector X, try to maximize it, okay? Because the vectors in the cube has every coordinate at most 1, right? But they could also be -1. So you pick it in a way that you get the L1 norm. And this is how it goes in general. If you want to understand the norm introduced by the polar body or dual body, you take your input F, you take your inner product with G for every G in your initial body, and you try to maximize it. Okay, that's like basic convex geometry. Now, what I want to do is I want to erase this example, and I want to ask you some other question. We also know this capital LP norms. I'm going to define them in a sec. And then these are defined by integrals. And there is some duality between LP norms. If 1 over P plus 1 over Q is 1, they are dual to each other. As I said, I'm going to define, don't worry if you have not seen LP norms before. Probably everybody has done, but But the question here is, in this capital LP world, it's hard to make sense of L1 and L infinity sometimes. What is capital L1? Not really clear. L infinity is maybe we have a better idea. It's kind of some maximization, but what is L1? So this is where I'm getting at. All right, so far, any questions? Okay, fantastic. All right, so this is now I told you some general convex geometry. Now I need to see it in my vector space of polynomials, right? And this is, goes after something called Veronese body. How does it go? You take all possible atomic elements, all these rank 1 people, and you put a plus and minus 1 in front of it so that it becomes centrally symmetric. For every vector, you also have the symmetric one with respect to the origin. Then you take the convex element, okay? And since this looks like this Veronese embedding, we call it Veronese body, but this is a convex body, right? Okay, it's centrally symmetric. So it gives you a norm from the discussion we just had. Every convex body which is centrally symmetric gives you a norm. What is the norm given by this object? And, for now, take my word that this object is kind of what handles the geometry of this object is kind of the central thread that handles all these rank problems that we are trying to think about. Okay, and this has a name. People call it nuclear norm. Okay, and roughly speaking, this is going to be our L1 that we didn't know how to do. Okay, so this, centrally symmetric, it gives you a norm. You get a polynomial which is not inside this convex body. You can try to scale it to get your polynomial in. It gives you a norm, right? This geometric way may not be so visible if you think algebraically, and there's a way to think about it algebraically too. And the way is this: when you are given a polynomial, you can find many ways to decompose it in terms of these atomic variables. It's not unique, you can find many ways, okay? But then what you do, when you decompose it, you take summation of absolute values of the coefficients here, right? And you have many options to decompose. You look for the minimal one, kind of the most economical one. And that gives you this nuclear norm, okay? And, again, so far, this is maybe a bit technical, but I hope the motivation was enough to make sense of it. So far, so good. So this is what it is. So this Veronese body gives you a norm, and it gives you the most economic way kind of to express your input in terms of these atomic objects, these rank 1 objects. Okay, so just an example. Let's say I got a polynomial written this way: half this guy, half the other guy, minus half. So this tells me the norm with respect to Veronese body, this nuclear norm, is at most 1/2 plus 1/2, which is 1. So it might be smaller because I just have one decomposition here, and it gives me 1, but I have to go for the minimal one, right? So it might be smaller, but I at least know by just this decomposition, the nuclear norm of this input is at most 1. Basically, this input is inside the convex body. Basically, that's what's going on, right? So if you think about this input, it's like I got this guy over here, an extreme point, another guy here. This is like 1/2 of the first one. Sorry, not 1/2. I apologize. So this is, I'm looking at this example. I got x1 to the d, xv2 to the d minus, you remember I put pluses and minuses in the definition, right? And I go take the line segment in between. This example F is the one in the middle. And literally this is inside the convex body. So of course norm is less than 1, but probably much smaller. Okay, so far so good. Any questions? You might ask, why do you go through all this geometry? Give us the results, but I think I need the language to state the theorem. And I'm sorry if, keep taking some time before stating the results. Any questions so far?
Well, I had a question, but I see that you're coming to it in the bottom of the slide. So
okay. Okay, great. So that means my slides are reasonable since it was able to, guess the question. So the inner product, I didn't define it yet. So, we had norms coming out of convex bodies, and to take the polar body, we needed an inner product. Here, you have many options on polynomials. The one that is somewhat standard is this thing called Bombieri-Weil inner product. And it goes as follows. There are many ways to define it, but one quick way is if you have this decomposition using monomials, then what you do, you take inner product of f and g. You take the coefficients, you multiply them, and every coefficient gets normalized by this combinatorial multinomial coefficient, right? And the multinomial coefficient is exactly as I wrote here. I'm talking about degree d polynomials. They're homogeneous, every term has same degree, and every term looks like x1 to the alpha 1, x2 to the alpha 2, xn to the alpha n, right? And when I sum up all the coordinates, they all have d. It's homogeneous. And this is my inner product. Okay, this might look a bit funky if it is the first time you're seeing it. This is a more or less standard Euclidean product. If you're somebody who works with tensors, if you take your Frobenius norm on tensors, use it for symmetric ones, this is what you're going to get. It's very natural. Okay, now what is this good for? It has these very nice properties. First of all, with respect to this inner product, every atomic element that I had has norm 1. They're all on the unit ball of this inner product, which is nice. Second, if I take any input f, if I take inner product with this atomic elements with respect to this inner product, this corresponds to pointwise evaluation. Your f evaluated at this particular vector v, v was somebody on the sphere, is equivalent to taking inner product of these two elements. Is this clear so far? Okay, and due to this property, we have a duality, which works very nice. Okay, and this goes as follows. If I define the infinity ball as the polynomials that has absolute value at most 1 on the sphere, okay, due to the second property here, this of course takes some time to think through it. This ball is precisely the dual of the tensor or of the Veronese body. Okay, so there is a duality between the infinity norm and the nuclear norm. Roughly speaking, infinity norm represents optimization. Okay, I'm lying tiny bit because I took absolute value, but not too bad. And then the nuclear norm kind of represents economic representation, so to speak, and they are dual to each other. Okay, Saugata, did this answer your question so far, or still?
Yes, it answered my question, but it raises one other question, which is, so this Bombieri-Weil inner product has important property of that it's invariant and orthogonal transformation of the variables. Right, exactly. And does the is it also true for this?
Veronese body, you mean, or the nuclear?
Yeah, for the Veronese.
Yeah, exactly, because it follows by the definition. Let me go back to the definition. So you take every vector on the sphere, and you take the corresponding, rank 1 object. You put plus and minus, then you take the convex hull, right? Before taking the convex hull, if you think about it, if you take a vector on the sphere, if you act on it with the orthogonal group, it's going to give you all possible vectors on the sphere. So it's going to go through all the extreme points of this Veronese body. It's basically convex hull of a group orbit, if you want to think about it that way. So it's by construction invariant.
Yeah, I see. Thanks.
Awesome. Thank you. So yeah, exactly. And this also helps because I want to do some LP norms, and they all go by integrating over the sphere. Okay, I think I'm almost done with this part. I'm close to showing you the results. Thanks for patience. So I also need to use LP norms. So, I give you theorems which will hold for any norm. But to be able to make them into algorithms, I need to be able to compute with these norms. So mathematically, I can state theorems, which will give you something with whatever norm you picked. And this Banach space theory people already figured out the correct invariance to think about these norms. But if you give me a very strange norm that I have no idea how to compute with, it doesn't help me too much for algorithms. So for algorithms, I can work with this LP norms, or here I wrote LR norms, which is you take a polynomial f, and to not get into very technical details, I want to use even things. Okay, so when I mean FR, I really mean F2R. Maybe I should do it this way to be fully precise. Anyway, so what you do, you take your polynomial, you raise it to the power 2r, say 2r is 4, 8, some number you like. You integrate it over the sphere. This is the uniform measure on the sphere. And then you take 1 over 2r, that is the definition of the norm. And for this, there is a whole bunch of work by numerical analysis people. The best I found was a paper due to Mauricio Velasco, very recent paper on arXiv. Velasco and Costancho, I think. Velasco and I think Costancho. I might be saying, I don't want to say his name wrong, so let me just say C. These are people from University of Los Andes in Colombia. Wonderful paper called Harmonic Hierarchies for Polynomial Optimization. And part of the paper, they developed this quadrature rules to explicitly compute this inner product, these norms that I'm talking about. So we have already machinery for this implemented on Julia. We re-implemented it in Python, etc., etc. So this is working out. So I can compute with these norms, hopefully. Okay. So what do we know about these norms? As your, norm, the subscript gets bigger, the norm gets bigger. And we have a better thing for polynomials. This is correct for any function, not only for a polynomial. For polynomials, we have an inequality due to Barwinock, which says, infinity is the biggest, of course, is getting bigger, but good, nice enough that you can compare with infinity with other ones from the other way around. So there is this interesting inequality. So you don't need to remember the inequality. What does it mean? As a punchline is this: as your norm gets roughly n log d, if you are dealing with homogeneous polynomials of degree d with n variables, your LR norm looks like the L infinity up to a constant. Okay, I'm not going to do anything like going up to n log d. I'm more interested in R when it is small, 4, 8, 10, some fixed number. Okay, but this is a nice fact. This tells you don't need to go all the way infinity when you're reasoning with it. Already at n log d, you're done. Okay. Now I can state my theorems. This is the first theorem. I'm going to state it for only LR norms. I have a polynomial in my vector space, and I have an LR norm. R is between 2 to infinity. You can pick anything you like. Then the approximate working rank of this polynomial with respect to LR norm is always less than equal to Bombieri-Weil norm of the polynomial squared divided by epsilon squared. Okay. The theorem statement might look a bit weird in the sense that the statement doesn't change with respect to the R. So I have the same upper bound for all of them. But the algorithmic part changes. So this is a correct statement for any LR norm. You can take infinity if you like. Mathematically, that's the strongest case. However, the way to compute this, at least the algorithm we were able to construct, the complexity of the algorithm changes depending on the norm you use. So as the R gets bigger, your estimate gets tighter and tighter. Your epsilon ball gets smaller and smaller. Okay. All right. So this is the theorem statement, true for any LP norm. And the algorithm we have, moreover, the epsilon approximate decomposition with respect to your LR norm can be computed by what we call randomized greedy approximation. It works as follows. It takes at most this many steps. This is where our bound comes from, but it can take much less. So this is an upper bound we were able to prove. Every step requires some sampling. All right. And then we sample, we do an operation, and we check the correctness. So you don't have to sample. You can go deterministic, but it will be much slower. Okay. So for your LR norm, you need to sample R to the DR times T. T is up to you here. T user defined. And I'm going to get to that. How does it change? Okay. You sample this many points, and you will do an operation that I'm going to tell you what it is. And it ends up being correct with this probability. And the correctness can be certified by just one single LR norm computation. Okay. And that's the algorithm. So I didn't tell you details yet. I'll come to that. But basically, the algorithm takes the upper bound many steps at most, possibly much less, but this is what we are able to prove, right? Every step of the algorithm requires sampling certain amount of vectors on the sphere, then doing an operation with them, which I didn't tell you yet. And then the more you sample, the probability of correctness of that step increases, but correctness is certified. So you do sampling, you do some operation, and you check if that was correct or not, and you go from there. If it is not correct, sample again, do it again. So basically, for this algorithm, main complexity parameters is how many vectors you sample, because that controls the complexity of the operation that you will do, which I will tell again later. and then the number of steps. The number of steps, we have a worst case bound. As I said, possibly you can get much better. Our estimate for the number of samples required changes with respect to R. So suppose your R is just 4, say, then you get 4 to the D. If it is 2, you get 2 to the D, okay? So if your D is big, you might say this is exponential, but usually you think about fixed degree polynomials. You have, say, a degree 10 polynomial, which is already big, degree 10. You know, you use L4 norm, your N could be anything. You see the number of samples does not depend on N, that's the strength. So it only sees the degree and the LP norm you're using. It does not change if you increase the number of variables. So that's something interesting here, right? That's my first algorithm. And it builds up the approximate decomposition along the way. We'll get to it again. That's my first theorem statement and first algorithm. If there are any quick questions I can take, and you can ask more after I present to you more details of the algorithm. So far, so good?
Yeah, sounds good.
All right, so this is the first theorem, and here's my second theorem. You give me any norm that you like, okay? And I'm gonna state the theorem for any norm. As I said, I cannot compute with arbitrary norms. Algorithm will be for the norms you can compute with, okay? All right, so the theorem statement is as follows. You give me any polynomial f, and there is something called type 2 constant of a norm. Don't worry about it. This is something tame. We have precise estimates on how big is it. Okay, there's some number. You pick the norm, I get a number out of it. And for LP norms, I have precise estimate. It's like roughly square root of p, which is small. Okay, for this is not something you should worry about. We have a theorem which says in the epsilon ball of your homogeneous polynomial or symmetric tensor, there will be somebody with rank bounded by the nuclear norm squared divided by epsilon squared. Okay. And since you are, measuring the distance with respect to some norm, you would expect the statement should change. And the only part that changes is this type 2 constant of the norm, which we can define later, doesn't really matter. Okay. All right. I'm going to try to tell you a little bit about the ideas behind type 2 constant. So that's what matters. And this representation can be computed as follows. This is more like, I called it Morey's sparsification because this is not like the first algorithm. First algorithm develops something from scratch. The second algorithm requires you give an input with some decomposition, whatever decomposition you give, right? And then the algorithm is very simple. It's a simple sampling algorithm, but the math behind it is not that simple. It finds a Q, which is epsilon close, and the working rank of Q is less than t squared times this squared divided by epsilon squared. And if you remember the minimal for this part, the minimal one was precisely the definition of the nuclear norm. That's where you get the theorem statement, okay? So if you are given the optimal decomposition, you get what was written in the theorem statement. If you are given something less optimal, you improve it, okay? So you might, of course, ask, can I already start with an optimal decomposition? Well, there are two things about it. One, this can be computed using semi-definite programming. A nice paper by Ji-Wang Ni, spells out the details. Nuclear norm for symmetric tensors, and one can also come and say, in general, this finding the optimal decomposition is an NPR problem. So there are two answers depending on which direction you're coming from. If you're somebody who wants to just compute, try to run the algorithm, there is an algorithm. But for this algorithm, for my particular algorithm, which we call the Morey's sparsification, we don't need to start with anything optimal. You give me something, we improve it by sampling. So this is a lightweight sampling algorithm, which gives you something, close to your input with lower rank, as long as your summation wasn't terrible. Okay. All right. So that's what it is. Okay. Then we did, as I said, everything from scratch. Then I searched here and over as much as I can to find something that is similar, because this is very natural. We shouldn't be the first people who think about it. That's what I thought. So I couldn't find anything very explicit, but I found two things that gets very close. So a paper by computer scientists, De La Vega, Canaan, Karpinski, and Vempala, they had a different way to think about the case only for L infinity norm, and they were not working with symmetric tensors, but more or less their theorem there, they work on completely different problem, constraint satisfaction. I think would correspond to this theorem for L infinity, more or less. But they don't have the algorithmic trade-off as we do. We work with any LP norm, and we have pretty good complexity if your LP norm is not too high. They only work with L infinity, which is the hardest case, because that's what was necessary for their application. And I found a paper by Destas Cuevas, Klingler, and Netzer. So they have at least the idea of like approximate decomposition, similar to this second theorem we have here. They only do it for a specific norm, Chatan norms, because their purpose was different. What they were thinking about was, here we are talking about approximate Waring rank. What they were thinking about was like, okay, I have different versions of rank for tensors, not symmetric, just general tensors. And if I allow jiggling, does this ranks look different from each other? That was what they were concerned about. They have applications in physics, that's their motivation. So this is the only two papers that I was able to find that has something similar. I couldn't find anything, with the generality and algorithmic results we have. If there's anybody, I'm happy to acknowledge, but this is what I'm able to find. Because this looks to me like a very basic question. I have estimates for exact, give me an epsilon room of error, how much I can improve. And this second theorem statement, as I said, holds for any norm. And this, I think, sharp. First is for LP norms, because the algorithm we have works with LP norms. Okay. And for the first one, if you want to use not LP norms, but the Bombieri-Weil norm itself, then we can do Frank-Wolf type algorithm, which I'm not going to be able to talk about today. Basically, like constraint gradient descent gives you the decomposition if you would like for the Weil norm. Okay. So far, any questions? I have about 7-8 minutes to give you a little bit about the idea. So if there are any questions, I can try to address. If not, at least I want to give you some intuition of how this stuff works out. So good. Okay. Okay, great. So here is the ideas. So first of all, this is our proposition that handles the number of samples that was required in this randomized greedy approximation algorithm. We had to prove the following. I want to find a vector on the sphere where the pointwise evaluation is bigger than half of the LR norm. Okay, you need to separate. So LR norm is going to be our cost function. You need to be able to find a vector where you evaluate it, it's bigger than that, okay, or half of it. And then what we proved using something called reverse Hölder inequalities in probability theory is if you sample this many uniformly from the sphere, right? And so this M here is, as you see, the number of samples I put in the theorem statement. If you sample this many, then you search for all of them and you look for the maximum one. It's going to be bigger than what you want with probability this. And you can check it by computing this LR norm and pointwise evaluations. If it is not satisfying what you want, sample again. All I'm trying to say here is this threshold, R to the RD, is the correct threshold to make it work with high probability. Okay. If you sample 4 times this, you have 1 to the, e to the -4, whatever. So T is up to you to pick, sample, test. When you find one of the VIs, we need only one of them, satisfying the property we want, algorithm runs. And here is how the algorithm works. You take the input, you give me an epsilon, you give me an LP norm that you like, LR norm. And I initialize by nothing, f hat 0, error infinity, and a vector space which is empty. Then what I do is this. At every step, I need to find a V where the pointwise evaluation of the polynomial there is bigger than half of the LP norm. Then when I find it, I enlarge my vector space by putting that atomic thingy inside. I take U union, this is union, the rank 1 object, right? Okay. Then what I do, then I take orthogonal projection of my input f on this vector space. I call it f hat. Then I check if I'm close enough. If error is less than epsilon, you stop. If not, you keep repeating. Okay. Then we managed to prove using this energy increment idea from additive combinatorics. This terminates. So let me show you the theorem statement back again. What we managed to prove is this process terminates at this many steps. And that gives you the upper bound for the rank of the object you create out of orthogonal projection. But maybe you can maybe terminate quicker, who knows? And the complexity you see comes from the sample size. And this is what it is. And the source that we learned this stuff is a wonderful paper called Zemeradi Regularity Lemma by Lovash and Zegheri. So they call it energy increment. This also Tao, covers all these additive combinatorics experts. That's the language they seem to use, and it was very useful for us to prove this termination criterion for this algorithm. Okay, that's my first thing. And my second thing is this Morey sparsification. You give me a decomposition, you give me your epsilon, you give me your norm. Then we create a measure on the discrete set 1, 2, 3 up to m. Okay, this algorithm is going to look like surprisingly simple. And the discrete measure weights I with respect to Ci absolute value normalized by summation of absolute values. Okay, then you set the sample size. Okay, you sample from this measure. All right, and then you construct. As I said, it's extremely simple. You take x, vis to the d, then you just take average of them. And if you're not close enough, you go back to sampling, you do it again. If it is close enough, you output your Q, that's it. And the proposition that you end up proving is this not being close enough happens with probability at most 1/4 because I put a 4 here. You can make it bigger, your probability will increase, right? Basically, the experts from local theory of Banach spaces back in the day figured out the correct thresholds. If you read their ideas, change them a little bit using this context, you can prove this proposition. All right. Wonderful. And let me see, I have 2 more minutes. Let me try to give you an idea of how this type 2 constant, Morey sampling, where does it come from? It's actually very natural. But before I give you the idea, is the algorithm and the statement is clear? I'm somewhat rushing now since I'm getting out of time, but I don't want to lose everybody. So ask me questions before I give you ideas in the remaining minute or two I have. So far clear, you get a decomposition, you create a discrete measure coming out of the coefficients you had. Then you know the sample size correctly due to a whole bunch of theory. Then you sample, you create your approximation, which is your QK. And as I said, it is deceivingly simple. You just take 1/k of these guys, right? You might find this very suspicious. Is this really correct, right? And if it is not close enough, you sample again. If it is close enough, you're done, okay? And what we say is this sampling, this QK is close enough with probability at least 3/4. If you put a 4 here, if you put a bigger number, the probability will increase accordingly. Okay. And I want to use a minute to give you intuition. As I said, this is in 70s in a French paper by Pizier, but he says the idea is due to Morey. These are Paris experts on Banach spaces at the time, right? So here's the idea. Suppose, I'm going to go simple. You can forget about this last minute. You can forget about everything else I said. At least take this, as an idea. Suppose you have a convex body which is given by, finitely many extreme points, A1, A2, AM. You take the convex out, okay? And then somebody hands you something in that convex body. Okay? Since it is convexal, you can write it as X lambda I AI, where summation of lambda I will be 1, right? And lambda I will be non-negative. That's the definition of a convexal, right? Okay, great. And then you create a measure like this. The measure is discrete. It takes the value vector AI with probability lambda I, right? what is the point of this? If you take expectation with respect to this measure, you end up getting precisely lambda I probability AI, and that is just X, right? So you created an expectation, you created a probability measure where the expectation is the point that you like. X is what you want to deal with. For me, X is going to be the polynomial I'm trying to decompose, right? Okay, now, in statistics, there's a whole bunch of ideas to estimate the expectation. Now the expectation is what you want by construction. Let's run statistics idea, which is just sample from this measure, take the average. It should look like your expectation with respect to the norm you picked, right? And then you end up proving the, this distance from what you constructed to what you wanted. This is this expectation, right? This is X. It's a random process, in expectation, this is less than this. This is this type 2 constant business. And after you have this proposition, you do some Markov-Chebyshev, whatnot, you get what you want. Okay, that's the idea. You create a probability measure where in expectation, it spits out what you want. And you use basically empirical method to estimate that expectation. And since the number of samples in your empirical method controls the rank for us, rank is the extreme points of my convex body. Extreme points of my Veronese body is precisely rank 1 objects, right? Then I end up controlling the rank. So this is a general idea if you want to write an element of a convex body in an economic way. All right, and that's it from me. Thank you so much.
Thank you, Alperen. So we have a couple of minutes for discussion. Any question for Alperen?
Right. It was a great talk. I already asked questions, but Ali, these recordings are available at some point, because maybe
Yeah. So I will post the link to the seminar website.
Right.
Yeah.
And yeah, hopefully this will be on archive before the end of the summer. So hopefully you'll have a written record too.
I'm looking forward to that. It was very interesting.
I mean, all the proofs, everything is ready, just writing it out. We are also implementing this first algorithm, randomized greedy approximation. We're also, getting a Python implementation of it. So hopefully they'll be available together.
So maybe I ask one question before I have to run, which is that, so one place where this Bombery-Weil norm appears, I guess it was there in your slides already, is this Cosland distribution.
Right. Let me go back to definition. Yeah, you're right.
So I was just wondering, from these different approaches that you talked about, have you considered random problems?
Exactly. So it depends on the variance of the randomness you create.
Mm-hmm.
So I looked up what, since machine learning people cares a lot about apparently these days in tensor decomposition,
mm-hmm.
I try to look up what kind of randomness they generate to test their algorithms.
Mm-hmm.
So some things I saw corresponds to don't take Cosland, but normalize all these coefficients by some maybe square root of the dimension. If you do that kind of stuff, these theorems will give you something much better than what we get in the worst case. So one thing I should say is, depending on the randomness, what we get may not be too impressive or not. So to me, instead of randomness, how I think about it is this. So let me try to go back to theorem statements. This is kind of a dynamic theorem. The algebraic geometry results we have is kind of blanket for any element of the vector space. So this theorem says, look at your input, and depending on the input, we have a different estimate. Right? So if your input has very large veil norm, Since what I'm able to guarantee goes by square root of the Weyl norm, this is not going to be a very impressive result, right? So I should be less than square root of the dimension to improve upon exact results. But apparently what people test is usually much less than that. So for that cases, what we give seems meaningful, right? So that's why it's like kind of apples and oranges to me to compare it with this beautiful algebraic geometry results. This is kind of a different flavor.
I mean, a related thing is that this Koszlin distribution is not the only orthogonally invariant Gaussian distribution on homogeneous polynomials. So what one can also do is once you have an inner product, you can look at the you can look at the harmonic decomposition,
exactly.
and then weigh if you weigh each one of them. But so then you get a whole kind of continuum of such. And Koszlin is somewhere at the edge or something, but depending on maybe different distributions are more interesting for the machine learning people.
Yeah, I mean, what they seem to be doing, I will try to dig more. That's part of my paper writing is delayed. I'm trying to dig on what they did. And the things I saw was they were scaling all of them by one scalar instead of doing what you just said, which is very, meaningful. You have this, irreducible decomposition with respect to orthogonal group action. Basically, that's what these harmonics are. And then you can scale them as you like. And you'll get a lot of, so the things I was able to find from last 2-3 years of this, ICML, NeurIPS, these conferences, they try to scale it all at once by something. And
that's interesting. I was not aware of.
Yeah, so yeah.
So the only thing I know about this business is that if you take the one extreme thing, like you put all the weights on the highest degree in this irreducible decomposition, then what you obtain is that the expected number of real things is much bigger than what you would get for Koszlin. So like it matches the complex.
I see. So it's like getting close to totally real kind of situation if you put it all.
Yes, exactly. I mean, the results are not, so they're still asymptotic, but.
Yeah, now that you say it, there was a paper of Antonio Lerario.
Yeah, exactly.
At the second
Lundberg,
Eric, I should go back and check with what we have. How does it compare to what they got? They had a very nice projection.
Exactly.
Okay.
Lerario, Lundberg, and Fyodorov, I think.
All right, I'll go look at that paper. Okay, thank you for reminding. Yeah, awesome.
Yeah, so it was a great talk. I'll listen to it again, but now I have to run because I have a meeting at 3.
It was a pleasure to meet you. Thanks a lot for questions.
Any other question? All right, if not, let's thank Alperen again, and thank you very much for attending our seminar. We will meet next week with the last seminar with David Sharping. And thank you, Alperen, for accepting our invitation. Sorry that we didn't have too much audience. I mean, this is the last, the final week of the semester at Purdue. People are almost around.
Yeah, that's understandable. I mean, we have a seminar today morning, and we had the same